Welcome to AI Peer Review. Today we're diving into a really interesting paper that's taking a fresh look at temporal action detection in videos.
Yeah, it's called DiffTAD, and it uses denoising diffusion, which is quite novel for this specific task of figuring out when actions happen and what they are in, long, untrimmed videos.
Exactly. Most methods we see try to, directly predict or regress action proposals. They set up anchors, refine boundaries,
Right.
the usual discriminative approach.
Right, but DiffTAD flips that. It's generative. It starts with essentially random guesses about time intervals, and then it refines them iteratively, pulling signal out of noise.
It reminds me a bit of how diffusion models work for images, going from pure noise to a picture based on a prompt.
That's a great analogy, and Figure 1 in the paper actually illustrates something similar. But here, it's video driving the process, and instead of generating pixels, it's generating action proposals by denoising these random temporal proposals.
So it's really leaning into this generative approach.
Definitely. It also aligns with this broader move towards one-stage detectors like DETR, trying to avoid some pitfalls of the older two-stage methods.
Okay, let's unpack that a bit. The traditional approach.
Yeah.
It often involves setting predefined anchors or predicting start-end times directly.
Yeah, anchor-based methods or methods predicting start-end boundaries. And while they work, they can have issues, maybe struggling with varied action lengths or needing complex post-processing.
And the shift towards DETR-style models and object detection was partly to get around needing things like complex anchor generation and NMS, right?
Exactly. To create simpler end-to-end pipelines, DiffTAD kind of brings that philosophy combined with diffusion into the temporal action detection space.
Okay, but applying diffusion models, which are known for being computationally, heavy, and applying them to video, which is already data-intensive.
Yeah.
That sounds challenging.
Oh, absolutely. There are definitely hurdles. One big one is just the inherent ambiguity in actions themselves. Unlike a clear object boundary in a picture, where does an action like running really start and end? It often blends into whatever came before or after. The paper calls it temporal momentum.
Right, that fuzziness makes defining the ground truth itself tricky, let alone training a model to pinpoint it perfectly.
Precisely. And then you add the computational cost. Diffusion models need those iterative refinement steps. Video analysis needs to process sequences, put them together.
Yeah, efficiency is a major concern.
Okay, so challenge is acknowledged. Let's get into the nuts and bolts of DiffTAD itself. How does this proposal denoising diffusion actually work? It starts random.
Yeah, it starts with random temporal proposals. Think of them as just pairs of start and end times drawn from a simple Gaussian distribution. Totally random guesses initially. The goal is to output accurate action proposals conditioned on the video's content.
And how does it learn to do that? The training process. So, during training, you start with the known ground truth action proposals. Clean start and end times. Then, you deliberately add Gaussian noise to them progressively over a series of time steps. This is the standard forward diffusion process corrupting the clean signal.
So you're basically teaching the model what noisy versions of good proposals look like at different levels of noise.
Exactly. And a key step here is how they represent these noisy proposals. They aren't just used as raw numbers. These discrete, noisy time points are projected into a continuous vector space using something called sinusoidal projection.
Okay. Why do that?
It makes them suitable to be used as queries for a transformer decoder, much like the object queries in DETR. These become the noisy queries the decoder works on. And the paper actually points out this design helps training converge faster, which is a nice side benefit.
So the way they frame the problem for the transformer is important too. It's not just throwing diffusion at it.
Right. The representation matters.
And then at inference time, when you have a new video and just random noise to start.
Inference reverses the process. You start with completely random temporal proposals, again from that Gaussian distribution. You feed these, projected as queries, along with the video features, into the train model. And iteratively, step by step, the model predicts cleaner versions of these proposals using the learned denoising function. It undoes the noise until you arrive at potentially accurate action boundaries and classifications.
Okay, that clarifies the core loop. Now, the architecture referenced in figures 2 and 3, let's break that down. It starts with a video encoder.
Yep, got to get features out of the video first. They use a pretty standard setup, a pre-trained i3D network for snippet features. Then, importantly, a multi-scale temporal transformer on top of that to capture longer-range dependencies across the whole video.
And they do this separately for RGB and optical flow. The paper calls it late fusion. That's interesting.
It is. A lot of methods fuse RGB and flow much earlier. Here, they keep them separate through the feature extraction and only combine the proposal information derived from each stream later on.
What's the thinking there?
The idea, supported by their results in Table 6 and Figure 7, is that RGB gives you appearance information and flow gives you motion information. They're complementary but distinct. By processing them separately for longer, the model might be better able to leverage the unique strengths of each modality for identifying actions. Early fusion might kind of dilute those signals.
Okay, treat appearance and motion as separate experts initially. Makes sense. And these global features feed into the detection decoder.
Right. The detection decoder is also a transformer, acting as the denoiser. And as we said, the queries it operates on aren't just learnable embeddings like standard DETR, they are those projected, noisy temporal proposals.
So the decoder takes the video context and these noisy time queries.
And predicts refined versions. The action class, the start 10 times, maybe an IOU estimate, and a completeness score for each proposal. It learns to map noisy time intervals plus video context to cleaner action predictions.
Got it. Now, one of the key innovations mentioned is this cross-time step selective conditioning. Figure 4 goes into detail. Sounds crucial for performance and speed.
It absolutely is. This is really about making the iterative denoising process smarter and more efficient during inference. At each denoising step, it looks back at the proposals predicted in the previous step. It calculates two things: how similar the features of the current noisy queries are to the previous step's predictions, and also the temporal IOU intersection over union between them.
Okay, so comparing based on both feature representation and actual time overlap.
Exactly. Then, using some thresholds 1 for similarity, Gela 2 for IOU, it selects a subset of the current queries. The intuition is like, okay, which of these current noisy proposals seem to be evolving consistently or overlapping well with what we thought was a good proposal in the last step? Focus on those promising ones.
Like pruning the search space a bit at each step.
Sort of, yeah. Or maybe better described as focusing refinement efforts. For the selected queries, it then fuses their key and value features with those from the corresponding predictions in the previous step. This fused information is then used to update the selected queries via cross-attention with the video features. It's a way to inject information from the previous refinement step in a targeted way.
Guiding the refinement process more intelligently.
Precisely. And they mention this is applied randomly during training, but to all proposals during inference.
And how does this differ from just standard self-conditioning you sometimes see?
Self-conditioning often just feeds the entire output prediction back into the next step's input. This is more selective. It uses that pairwise similarity and IOU check to choose which proposals get this extra conditioning information via feature fusion and attention. It's more targeted.
Okay, that makes the distinction clear. Now, thinking about training again, algorithm 1, we mentioned adding noise. Anything else notable?
Yes, the noise addition follows a standard decreasing cosine schedule for ECT, which controls the noise level. But interestingly, they found they also needed to scale the ground truth proposal coordinates, and the optimal scaling factor was different for TAD compared to object detection. Table 4 shows TAD favored a lower scaling value. It highlights that you sometimes need to tune these diffusion parameters specifically for the task, not just borrow directly from image domains.
Another nod to the specifics of temporal data and the loss function. It's like DETRs.
Yeah, they use a set prediction loss. Since the model outputs a variable set of proposals, you need a way to match predictions to ground truth actions. They use the Hungarian algorithm for this optimal transport assignment, just like DETR. It finds the best one-to-one matching between predicted and actual actions so the loss can be calculated properly.
Right, handling the unordered set prediction problem. Okay.
Yeah.
And for inference algorithm 2, it uses DDM.
Correct. During inference, they use DDIM, Denoising Diffusion Implicit Models. It's a technique that allows for faster sampling from the diffusion model. Instead of needing hundreds or thousands of small denoising steps like the original DDPM, DDIM lets you take bigger jumps, getting good results in, say, tens of steps. Makes inference much more practical.
So start random, project to queries, feed to decoder, get predictions, use DDIM to estimate the next slightly cleaner set of proposals, and repeat.
That's the loop. And at the very end, to get a final confidence score for each action proposal, they simply average the predicted action classification score and the completeness score.
Simple averaging. Okay, let's talk results and insights. Figure 5 and the tables look packed. First up, one model, multiple trade-offs.
This is super useful practically. Figure 5b and Table 5 show that after you've trained the DiffTAD model just once, you can choose how many initial random proposals to start with and how many DDIM sampling steps to run at inference time.
So you can tune it post-training.
Exactly. Want it faster. Use fewer proposals or fewer steps. Need maximum accuracy. Crank them up. It gives you flexibility without retraining, which is a big plus. You can tailor it to your resource budget or latency requirements.
That's a really valuable property. What about faster convergence in Figure 5a? DETR models are notoriously slow trainers.
Yeah, that's a common headache. The paper argues DiffTAD converges more stably and often faster than, say, a baseline built directly on DiffusionDet, an object detection diffusion model. They attribute this partly to that query design we discussed, the projected noisy proposals acting as better, more informative anchors from the start. It seems to stabilize the Hungarian matching process, too. Figure 5a shows this visually.
Okay, mitigating a known pain point and the better sampling point. Table 1, Figure 6a.
This shows performance generally improves as you increase the number of DDIM sampling steps. More refinement helps. Interestingly, they note that unlike object detection, just throwing more initial random proposals at the problem doesn't help as much for TAD. Maybe because actions are sparser in time than objects in space?
Plausible. So quality of refinement, more steps, matters more than quantity of initial guesses here.
Seems that way. And the gains from more steps are quite significant compared to refinement in traditional models.
And how effective was that cross-time step selective conditioning in practice? Figure 6b, Table 2.
Very effective, it seems. Figure 6b shows a clear correlation. The more you use this conditioning during training, the better the performance. And Table 2 directly compares it against simpler alternatives like basic feature concatenation or the proposal renewal strategy from DiffusionDet. The selective conditioning comes out significantly ahead.
So that specific mechanism is really pulling its weight.
Definitely looks like a key contribution.
Table 3 looks at the impact of sampling decomposition. What's that about?
They basically break down the gains. How much improvement comes just from using DDIM for denoising versus how much comes from their selective conditioning? The takeaway is that both help, but selective conditioning is particularly effective. Combining them gives the best results. They work well together.
Okay, and we touched on optimal signal scaling, Table 4, and late fusion benefits, Table 6, Figure 7, both showing task-specific tuning and architectural choices matter. What about being NNS-free in Table 7?
This is another benefit linked to the selective conditioning. Because that process helps produce sparser, less redundant predictions, they find they don't actually need non-maximum suppression NMS afterwards.
No cleanup step needed.
Apparently not much, or none. Table 7 shows performance is similar with or without NMS, unlike many other methods that rely heavily on it. That simplifies the whole pipeline.
Definitely simpler. And finally, the ablation of denoising strategy in Table 8, corrupting boundaries versus labels.
Yeah, they checked. Is it more important to teach the model to denoise the action's time boundaries or its class label? The results strongly suggest denoising the boundaries is the critical part. Performance drops significantly if you only corrupt labels. It seems the diffusion process here is primarily learning temporal localization.
Fascinating. So the core strength is figuring out the when. Now the big question, how does DiffTAD stack up against other state-of-the-art methods? Table 1 compares them.
On Thumos, it performs really well. It significantly beats strong discriminative methods, especially when you look at stricter IOU thresholds, meaning it's getting the boundaries more precise. It also clearly outperforms that adapted DiffusionDet baseline.
So, strong showing on Thumos. What about ActivityNet?
ActivityNet is generally tougher. DiffTAD is competitive, not necessarily #1 across the board, but it marks a big improvement for DTR-style approaches on this dataset. It closes the gap significantly compared to prior generative or DTR-like methods, and again, much better than the direct DiffusionDet adaptation.
Okay, so summing this all up, DiffTAD feels like a genuinely new direction for temporal action detection.
I think so. It's leveraging diffusion models in a smart way, moving away from direct prediction towards this generative refinement process.
And starting from random proposals, iteratively cleaning them up. That's quite a paradigm shift.
Yeah, absolutely. And coupling that with innovations like the selective conditioning for efficiency and accuracy and the effective late fusion strategy, it seems to address some real challenges.
The benefits, like better convergence, the accuracy-speed trade-off, flexibility, being NMS-free, those are tangible advantages.
For sure. It's a great example, like you find in AI peer review, of cross-pollination ideas from image generation sparking progress in video understanding.
It definitely makes you wonder, what other video tasks could benefit from this kind of generative, iterative refinement approach?
Exactly. Or how can we further tailor diffusion processes specifically for the nuances of temporal data? There's likely more to explore there.
It certainly pushes the thinking beyond just discriminative classifiers or regressors. A lot to consider. Well, if this deep dive into DiffTAD caught your interest, definitely check out the paper itself. The ablation studies are quite detailed. Think about how these generative ideas might apply to challenges you're working on. Thanks for joining us for this discussion on AI peer review.